Remember the question that we all started our discussions from? 3 houses and 3 utilities. And we say it is not possible for us to construct roads from these 3 houses to these 3 utilities such that roads do not cross each other. You keep trying, you don't succeed is not the reason why this doesn't happen. If you think this doesn't happen, you need a solid proof to say that this particular thing doesn't really happen. How do you do that? Let me first write down what is this graph. It has 3 dots here and 3 dots here, and every dot connects every other dot. Correct? This is the structure. And it's a bipartite graph, as you know. It's a complete bipartite graph. That's what you mean by K33. Now look at this. We know a small result. That a bipartite graph can never have an odd cycle, and in particular can never have a cycle with 3 vertices. A triangle is never visible, which means the same old result, 3r is less than or equal to 2e, might hold good here if it is planar. But then 3r, you see how we got this in the previous proof? That's because every region was bounded by at least 3 edges. But in this case, we are sure that it is not just 3 but 4. Which means the entire theorem holds good, but we can indeed write this as 4r is less than or equal to 2e. Pause and think if it's not clear why this is true. If you have followed the proof of 3r less than or equal to 2e, you will know why, given a bipartite graph, it is always 4r less than or equal to 2e, provided the graph is planar. Is the graph planar? If the graph is planar, it implies that 4r is less than or equal to 2e. Let us write this down. If the graph is planar, then it implies that 4r is less than or equal to 2e. Also, if the graph is planar, we know that v minus e plus r is equal to 2. I am also saying that 4r is less than or equal to 2e. Let us club these two things together and see what we get. Now, r is equal to 2 plus e minus v. I am just rewriting v minus e plus r equals 2. So, instead of r, we can write 4 times 2 plus e minus v. This has to be less than or equal to 2e. Let's see if this is true. 4 times. So what I did was I just got rid of r because I don't know what is r in a K33. But I know what is v and e. Correct? That's the trick. If you didn't follow, don't worry much. But the point is we have to somehow show that if the graph is planar, then it implies something, and finally a contradiction. Right? So 2 plus the number of edges here is, let us count, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 by 2. The sum of degree is 18 by 2 is the number of edges. So you can even count the number of edges. Manually, the number of edges happen to be 9. The number of vertices happen to be 6. So you see what you're getting here? Whatever is the number, less than or equal to 2 times the number of edges, which is again 9. Is this true? Let's see. 4 times 11 minus 6 is 5. And this happens to be 20 is less than or equal to 18. I mean, what on earth is this? Where in the universe is this inequality true? Do you think 20 is less than or equal to 18? It's absurd. Let's write that down. It is A-B-S-U-R-D. Absurd. What is absurd? The fact that 20 is less than or equal to 18. So what? So what? You trace back and see how you started. You started with the fact that the graph is planar. And that implies absurdity, which means the fact that the graph is planar is not in fact true. Which means the graph is not planar. Which means K33 is non-planar. Which means you cannot, in the lifetime of this universe, try to construct 3 houses to 3 utilities, all possible roads, such that roads do not intersect each other. Don't even try to do it, you will not succeed. Remember? This story sounds familiar. In Königsberg Bridge, we told you that don't even try to traverse this path. You will not succeed, and we gave you a mathematical proof. Just summarize, look at the beauty of this result. You don't have to keep trying, and then go breathless and say this is not possible. All you got to do is analyze mathematically, you'll get some absurdity, and hence the graph is not planar.